Hello everybody. So now after the discussion on the log scale, we can start the discussion on the Moody diagram, a Moody chart. A Moody chart is one of the very most commonly or widely used charts in fluid mechanics, and it's used for the same purpose of that we use Colebrook equation for, which is calculating the friction factor uh, based on the value of Reynolds number and the relative roughness. So this is a chart that is drawn on a log scale, and you can see this is log scale on y-axis and log scale on x-axis. The x-axis is Reynolds number, and this is what you can see here. And Reynolds number ranges from 10 power 3 almost all the way to 10 power 8. So it's 5 orders of magnitude from 10 power 3 to 10 power 8. I mean, the power increased 5 times. So it's a very wide range here. And you'd see here that the Reynolds number range is a range that includes laminar and turbulent flow. And this is why we have here this region, which is highlighted here. It represents the laminar flow region, which is Reynolds number less than around 2500 or 2400 almost, which is the laminar flow region. Then we have the transitional flow, which is between 2000, almost 2000 to 4000, and more than 4000 is what we consider as a turbulent flow. So this is the range of Reynolds number, and for the laminar flow we have a relation which is 64 over Reynolds number. This is what it says here. So this 64 over Reynolds number is for the circular pipes, as we discussed before in the previous videos. So you can calculate it directly, or you can get it from the chart. So it's valid for both laminar and turbulent flows. For the Reynolds number, we have ranges in the turbulent flow that depend on two factors. Here it's only a function of Reynolds number, so we have only one line. In turbulent flow, it's function of two variables. The Reynolds number is one of them, and there is another variable which is the relative roughness. So we have different lines here, a set of lines that have different values of or each one has a value of epsilon over d. So here this is for smooth pipes where epsilon is 0. So this is this line, and notice that these lines are curves. So this is the smooth pipe, and as the surface roughness or the relative roughness increases, we have different lines. So this is 10 power minus 6, then 5 times 10 power minus 6, then this is 5 times 10 power minus 6, then this is 10 power minus 5, which is this line, then 5 times 10 power minus 5, 10 power minus 4, and so on until 0.05. So these are the relative roughness, and of course, as the relative roughness increases, the friction factor will increase, and this is very logical. Smooth pipe will have much less friction factor than rough pipes. So it's a very logical thing that we have increasing friction factor with the increase in the relative roughness. There is a point that is worth mentioning here, that the numbers here correspond to curves. So it's not like y-axis. These each one of these numbers represent one of these curves. So it's not y-axis. So let's say it's 2 times 10 power minus 4. So this number doesn't represent a horizontal line. It represents this curve. So it goes up this way. Okay, so it goes like this. Okay, so this is the 2 times 10 power minus 4. So sometimes you would get confused and think these are values of y-axis or a secondary y-axis. It's not right. It's just representing one of these lines. And to make it easy for us to understand the number without having issues with the grid lines, the numbers are written beside the chart, but this doesn't mean that this is y-axis. So I hope it's clear. So the way we use this chart is simply you find the intersection of the two parameters, the Reynolds number and epsilon over d, and from the intersection of these two values we get the friction factor. So let's try an example. Let's say we have Reynolds number of, let's say, 10 power 5, which is 100,000, and relative roughness of 2 times 10 power minus 3, for example. So Reynolds number of 10 power 5 is here, so it's this, it is this line, okay, which is this line, and 2 times 10 power minus 3 is this curve. So if you look for the intersection of these two values, is going to be this point here. So this is Reynolds of 10 power 5, and this is epsilon over d of 2 times 10 power minus 3. So this is the value. So if you want to find the corresponding value of the friction factor, it's as simple as just looking at the y-axis. So we go to the left, so this is the point. We go to the left, and by going to the left we'll find that it's 0.025. So this is how it works. So it's simple. Just need to be familiar with the chart. You know how to use it well, and you can get the values very easily. And you notice here that this is much easier than the equation. You don't need to do any calculations or iterative solutions or anything. You just pick the values from the chart and find the intersection and go find the friction factor. Of course, this is not going to give accurate results as the Colebrook equation. Colebrook equation will give much more accurate results, but it requires either long calculations or a software or a tool that you can, or a calculator that can do the solution to this equation. So this is the trade-off. So here you get the value easily, but you need to put more time, or you need to sacrifice a little bit the accuracy. So it's not going to be very accurate, especially if you have a value that's not on the of one of these graphs. So let's say you have 3 times 10 power minus 3. So this is 2 and 4. You don't have 3. So you have to go for something in between. It's a bit hard that you get the accurate value, but you can get something that's really close. Let's say you have 55 times 10 power minus 3. So it's going to be between these two and closer to 0.006. So it's going to be somewhere here. So it's not always accurate, depending on the values that you have, whether they are among the lines that you have or not. But anyways, it's a good way of finding the friction factor with acceptable accuracy, if you are doing it in an accurate way somehow. One last thing about this chart is this dashed line here, which says fully rough turbulent flow. So this has nothing to do with extracting the data from the chart. It just gives an idea about the effect of Reynolds number on the friction factor. So for the roughnesses more than 5 times 10 power minus 5, starting from this and going up, the friction factor kind of levels off, so it doesn't decrease with the increase in Reynolds number. So you see in this range it decreases as Reynolds number increases, okay? But after this dashed line, the value almost stays constant. So for let's say 10 power 6, it's almost the same as 10 power 7, almost the same as 10 power 8. So it doesn't change with the increase in Reynolds number. So this is what we call the fully rough turbulent flow, or sometimes we call it wholly turbulent flow, which means that it's only function of epsilon over d. It's not dependent on Reynolds number anymore. So this is this dashed line, the function of this dashed line in the graph. But at the end of the day, it's not going to affect the way you extract data from the chart. So the other chart that we have here, it's just from another textbook, but for me this is more clearer than the previous one. This has a different background color of the grid lines than the lines themselves. Here it's very close in color. It doesn't have the roughness table here, so it makes it sometimes difficult to extract data in this range, while here it's not. So I prefer this to that, but at the end of the day, it's the same data or the same chart, but written in different colors. So anyways, this is all what I want to cover here. Inshallah, next video I'm going to show you how to solve the Colebrook equation using Microsoft Excel, and based on this you'd see how to do this iterative solution using the Microsoft Excel software, and at the same time I would solve the same examples using the chart, so you see how to get the values from the chart and compare this to what you get from the equation. So I hope this would be helpful to you and a good way of getting more practice on using the chart. So I'll see you then, inshallah. Goodbye.